Okay, so the next thing for today, which is the last thing for today, is optimization. And after this, we have only quadratic inequality left, and we don't have any business with quadratic anymore. The only thing the HL will do in addition to this is the cubic and quartic and all that. For SL, you have also, gotten this part done. Okay? Now, optimization. When we talk about optimization, we're talking about maximum and minimum, trying to maximize something or minimize something. I'll give you an example. In your Form 4, did I teach you guys linear programming?
Yes, I remember that word.
So I taught you. Inequality.
Yes.
Maximum profit, feasible region. What we are trying to do also in linear programming is trying to solve optimization problem. Now when we say optimization problem, optimize to make it better, to get the best deal. If you are a manufacturer, what is your best target for you? What in what sense?
Low cost, high product.
Low cost in production and more profit. So your own optimization problem is either to maximize your profit or to minimize your costs. Okay? Let's now bring that context into quadratic. When we're talking about optimization problem, we are talking about finding the maximum or the minimum of that function. There's a function, right? So there's a function y equals ax squared plus bx plus c. Okay? This function is represented in your xy plane. If this is your graph, this is the maximum value of y. Do you agree? Do you agree?
Yes.
And the maximum value of y occurs at a particular value of x. Okay? So getting this maximum or minimum value is called optimization. Getting this maximum or minimum value is what we call the optimization. Am I making sense now?
Yeah.
One thing is this. We are lucky we have done enough groundwork already. So there's no need to go over this again. In fact, when I taught my Form 4, current Form 4, how to use quadratic to solve optimization problem, the first thing they'll do is to write this in this form. Remember we did this also, computing the square, right? So let's call this m, then minus n. Remember this? The first thing is to be able to write it in this form, because we know that at the vertex, x is equal to negative m, and y is equal to n. Do you agree?
Yeah.
And this will be your vertex. But then they have to spend some time to go from this step to this step, right?
Yeah.
In order to get the vertex. And once they get the vertex, this is the maximum or minimum value, the y value. This one. Or in this case, this part. This will be the value. Okay? Talk to me, please. Understand?
Yes.
But for this class, do we need to express this in this way before you can get this vertex?
No.
We have done something,
Yeah.
right?
Yeah.
Which is what? What is x at this point? That is it. That's why I said we have done enough groundwork in this class. So there's no need to go over it like we are IGCSE students anymore. So I'm just going to play you this example. Then after that, I will write maybe a short note, or just ask you to write what we can see in that book, and that's it. And I'll give you the other worksheet. Alex, is there a problem? Sometimes the way you sign in my class.
In this question, we consider finding the maximum or minimum value of a quadratic function, depending on whether it is concave down or concave up. This process is called optimization, because we are seeking the optimal value. For the quadratic function in part A, the coefficient a is 1, which is positive. The graph is concave up, so we are trying to find the minimum value of the function. The minimum value occurs at the vertex, which lies on the axis of symmetry, x equals minus b over 2a. So the vertex has x-coordinate minus a half, and we substitute this value to find the y-coordinate. Be careful with negative substitution. So the minimum value of y is minus 3 1/4, which occurs when x equals minus a half. For the quadratic function in part B, the coefficient a is -2, which is negative. The graph is concave down, so we are trying to find the maximum value of the function. The maximum value of the quadratic occurs at the vertex, and so we substitute the coefficients to find the x-coordinate is 3/4. We substitute this value into the function to find the y-coordinate. So the maximum value of y is 4 1/8, which occurs when x equals 3/4.
Does this make sense? So it's that easy. There's no need to write in form of completing the square, then interpreting this. There's no need. Your a value determines your maximum or minimum. Remember, when a is negative, you're dealing with maximum type. And when a is positive, you're dealing with the minimum type. It's like a opposite, like a swap. So don't think, oh, maximum is when a is positive. No. Do you understand that? You have to be very careful. It can be misleading sometimes. Okay? And once you identify your a, of course, you don't have to sketch like this. You can just say, oh, since a is greater than 0, the graph gives a maximum or something like that. Just write in your own words, but write something convincing. Write something that tells me you know what you're talking about. And if you're okay with this explanation, please go for it. Understand? Oh, since a is greater than 0, then the graph has a minimum point or minimum value. Remember, if there's a minimum point, it means there's a minimum value. Because the point includes the x-coordinate and the value itself. Okay? Your point is xy. X is the value of x at that point, be it minimum or maximum. Y coordinate of that point is the value itself. Am I making sense, please?
Yes.
Yes.
So this is all. The next set of questions is just more application. So I hope this is the last one. Yes, this is the last one. So let me play this for you also. So you can see another application in different scenario. It's better to play the audio because we don't have time. I thought I played. Okay, I did not.
In this question, we have information given to us in sentences, and we have a diagram to help us. We see the question has 2 parts, and it is a good idea to read both parts before you start answering the problem. We are given information about a rectangular garden plot. We are asked to write an algebraic expression for its area,
One sec.
and then optimize the area by choosing. We are given information in this question.
I think we should read the question first, so we understand what we are doing. Because the question is not being read in the audio, okay? So let's try to understand. The reason why I started with what problem is because of questions like this. So we don't want to jump into optimization directly, but we want you to be familiar with how to write algebraic equation from what problem, how to solve, so that it's easier for you when you get to this point. Am I making sense? Yes. So, a gardener adds 40 meters of fencing to enclose a rectangular garden plot. The fencing could be in form of a wire or a form of wood. Okay, that fencing is 40 altogether. But of course, you're not going to fence where the wall is. So it means you're only fencing this part alone, 3 parts of it. Okay? So again, like Anson said earlier, it's always good to have a picture to give us, to bring alive the context of the question. Understand? Sleepyhead.
Yeah.
Okay. Now, suppose the 2 new equal sides are FCM long. Show that the area of the enclosed is this and find the dimension of the maximum area. What does dimension mean? The length and the width. Understand? So when we say dimension, it means they're asking you for the length and the width. Something like, oh, this rectangle is 4 by 7 meters. 4 meters by 7 meters. That is the dimension. And we write it to look like times. I'm sure you have seen that a lot. Somebody writes 2 meters by 1 meter. This is dimension. It's not 2 meters times 1 meter. Pronounce this as by. Understand? Okay, so now let's listen to the audio. And that's all for today.
We have information given to us in sentences, and we have a diagram to help us. We see the question has two parts, and it is a good idea to read both parts before you start answering the problem. We are given information about a rectangular garden plot. We are asked to write an algebraic expression for its area, and then optimize the area by choosing the correct dimensions of the rectangle. On the diagram, we label some points X, Y, and Z, so it is easier to refer to a particular side of the fence. We are given that the two equal sides of the fence have length X meters. Since the sum of the length of the three sides is 40 meters, the side XY must have length 40 minus 2x meters. The area of the garden is the product of its length and its width. We write these lengths in terms of x to obtain the given expression. To find the garden of maximum area, we could expand the brackets and use the vertex. However, it is quicker to notice that when x equals 0 or 20, the area of the garden is 0. These are the x-intercepts for the graph of this quadratic. The vertex lies midway between these values, and therefore has x-coordinate 10. The coefficient of x squared is negative, so the graph is concave down, and the vertex does indeed represent the maximum value of the quadratic. When x equals 10, the length of the side xy is 20 meters. So, the area is maximized when yz is 10 meters and xy is 20 meters.
Does this make sense?
Uh-huh.
Remember, it's talking about show that the area is this. This is already our x. Remember, the entire fencing is 40.
Yes.
So which means this unknown, we said earlier, there's no need to call this y
Yeah.
if they are all related.
Yeah.
And the relationship is that addition of everything is 40. So which means this is just 40 minus these two. And that's why you have this. Because without this, you cannot be describing your area. You know your area is what? Oh, area is unknown. Area is an expression we want to get, right? So from this, your area is length times width, which is going to be this product. And that's the first thing to be shown. Find the dimension that maximizes the area. Okay? Find the dimension of the maximum area. What dimension makes the area the biggest possible? Because of course, you can have different areas, depending on what you use this for, how long you make this. You understand what I'm saying? You can have different areas. But what dimension will give you the biggest possible area? Do you understand what I mean? So, of course, when you solve, why are we solving? Joey, this is the function, right? This is the function. The reason why this is being solved, in case you do not know, the author of this book is trying to picture the entire graph. You can say that x is negative, x coefficient of xy is negative, so we know it's this form, right? The author is telling you to picture the point of intersection with the x-axis. This is the shape of the curve, do you agree? So if it crosses x-axis, where does it cross x-axis when this area is equal to 0?
Yes.
This graph represents the area function.
Yeah.
Instead of y is equal to, this is a is equal to. So this graph represents a. So when a is equal to 0, x is either equal to 0 or 20. So basically, this is the xy plane. Why is this important? Because you can always get the axis of symmetry by adding these two together. That's the reason. Hello? That's the reason. If you look at it, this is, let's write that. So a is equal to 40x minus 2x squared, right? Which is going to be minus 2x squared plus 40x. In that case, your c is equal to 0. If you don't want to do this, what is the value of x at the vertex? Negative b over 2a. Let's substitute. What is your b in this case? So minus 40 over 2 times what?
-2.
So which is minus 40 divided by negative 4, which gives x is equal to what?
10.
And that is the same as the midpoint of these two. So you see that you use your geometrical picture to analyze it, which is what has been done. Or you just go about what we have done before. Either way will be fine. We didn't learn those two things because they are going to lead to different solutions. We learned them so you can realize that even though there are different parts, everything still leads to that solution, which is finding the vertex. Understand? And once you find your vertex, it means, oh, at this maximum value of A, x is equal to 10. So the only thing left is, what is going to be that A for x is equal to 10? And that is why there will be the, oh, we don't need that value of the area. The question is not about value of the area. The question is about what is the dimension that gives area as the maximum, which means what is going to be the x and the other one. X is just this one, right? The other one is this, which is 40 minus 2x. Hello, are you getting the point?
Yes.
But x is the key to everything. Once you get your x, you can get your xz. Your dimension is to find xz and yz. Am I making sense? And yz is just your x. So to find the other one, this is yz, which is x is equal to 10. So which means if you want to find the maximum area, yz must be 10 meters. And then xz must be, because it is 40 minus 2x, it's going to be 40 minus 20, which is 20. So it means the dimension that gives the maximum area is 20 meters by 10 meters. That's the point. Does that make sense? So it means the dimension that gives the maximum area is 20 meters by 10 meters. So what is the maximum area itself?
200.
200.
Meters squared.
Because if this is the length and this is the width, and we're talking about the rectangle, that is it. And that 200 can be extracted directly from here when you put 10. Hello? Does this make sense?
Yes.
Just giving more information. Any questions? So with that, I have 4 sweet questions here. The last one is a bit challenging, but I'd like you to try. Then we will do it together if you don't get it. All right? Any other question before we stop our recording? So if there's nothing, thank you very much, Ms. Joey.